Okay, so welcome back. And so what I'm going to discuss shortly, or in this short video, is the idea behind decomposition. Now, the important part of using partial fractions is anticipating the form that the rational function will take once you do the decomposition. The great news about using this technique, it is both predictable and highly dependent on the factorization of the denominator. Okay. Now, one thing you need to know is, in order to apply this technique, you got to be careful with this one, because if you don't, then you run into problems. Okay. So this technique works as long as the degree of the top is less than the degree of the bottom. Okay? So as long as the degree of the numerator is less than the degree of the denominator, then this process, this technique of partial fractions will work. Well, what if we have the situation where the degree of the top, is greater than or equal to the degree of the bottom? Well, in that case, we're going to have to divide. We're going to have to use long division first. So if this is the case, then you have to use long division to rewrite the rational function with a quotient plus a remainder. Okay? So if we do, then you're going to end up with a quotient. So for example, we might end up with equal to some rational, some function, right, plus a remainder. Okay, so if the degree of the top is bigger than the degree of the bottom, then we're going to use long division to rewrite this rational expression as a function plus a simpler, proper rational function where the degree of the remainder, r, is less than the remainder of q. Okay, so then we can use partial fractions on this piece, and then of course we should be able to integrate this piece easily. Okay, and that's it. So let's do an example to show you how this process works. Now, the next example I'm going to do, you don't need to use partial fractions, but I'm going to use partial fractions just to show you. Okay, see you next time.